Thank you. So, hi everyone. My name is Wang, and I'll talk about some topics around Bayesian. So, if you have any questions, feel free to add in chat, or I'll read out your question while presenting. All right. So a little about what the problem is. Basically, for Bayesian, we care about black box function optimization. So imagine, like, for example, you might have a robot and it's sort of complicated and has a lot of like different kinds of parameters, like the control parameter or how long the legs are, things like that. And in order to really make it work, you have to sort of try different kinds of these parameters and make it walk like as fast as possible or as stable as possible. So either way, you're going to have an objective, and we're going to call it function f. And the thing is, we are sort of viewing this as a black box because we don't know much about, like, within this black box, how this parameter impacts our robot. And eventually, the goal is to try different hyperparameters sequentially so that we can get to a very good setting as soon as possible. And well, more formally, the goal is to find the argmax of function f by sequentially evaluating it. So this kind of problem actually appears in a lot of different scenarios. For example, in autonomous driving, we also have a lot of parameters to tune, which have a very big impact on how well it performs. In biology, for example, when people do something like gene design, it exactly follows this paradigm where it's really about how you design the experiment in order to find the gene that you want. And similar things happens in, well, molecular design, or and also, like, I'm not exactly sure what the audience's background is, but a lot of people really care about hyperparameter tuning and machine learning, because exactly like these various different kinds of problems, we also have a lot of hyperparameters like learning rate, momentum, well, the size of the network, etc., and they have a big impact on how well the model performs. So our goal here is to show that, okay, can we test well, hyperparameters in a sequence so that eventually we get a very low empirical loss, or like validation loss. And all these problems share some similar challenges. The function f is quite expensive to evaluate. Well, training machine learning models take a while. Doing wet lab experiments also take a long time. And sometimes these type of evaluations can take days. Well, second, f is actually a multi-peak function, which means that it doesn't only have one peak. It might have like several different peaks, which makes the global optimization problem more difficult. Third problem is that, well, we don't really have gradient information. Suppose we're trying to access the validation error of a network. Well, we don't really try, well, in these cases, we don't really have exactly what the gradient is. And similarly, it goes, this problem goes to like robotics and these biology type of problems. And so fourth is that the evaluations can be quite noisy. And as you can see in robotics problems, or even like machine learning problems, depending on what exactly your machine status is, or like the random seed, you might have a slightly different evaluations. All right, so from all these, well, I must say that for gradient information, in some situations, Bayesian optimization can actually make use of gradients, but this is not really within the scope of this talk. All right, so so thinking about like how to solve this problem, one really simple approach could be that we use grade search, and that is indeed the type of solution that a lot of people adopted when we are facing hyperparameter tuning method problems in machine learning, and we're basically trying to take a grade and then evaluating them one by one. The other approach is saying, well, we can do random search. It has been shown that random search could be better than grid search, but we are still missing a lot of good points because we're not really utilizing any information of what has been evaluated before. So, right, exactly. The problem is that a lot of evaluations are actually wasted in this case. And here's actually where Bayesian optimization comes in. It's really a method that tries to be smarter about how to choose the points to evaluate. And here the key idea is we're trying to build a probabilistic model of the function f. And then we're going to use this probabilistic model to decide where to query decide where, how to choose the query points that we're going to evaluate. And once we choose these query points, we're going to update the model and then do the same loop. So there are a couple of questions in this particular idea. So one is what we do with the probabilistic model. And here, well, notice that we're actually doing a probabilistic model for functions, which means we're trying to derive a distribution over functions. And the second problem is how do we choose the query points? And typically in Bayesian optimization, the way we do it is by using a decision criterion, which we call the acquisition function. And it really makes sense because it's the way we acquire information. It's the way we try to acquire more data, and that's why it's called the acquisition function. So in the end, the idea here is that we are trying to transform our global optimization problem of an expensive and difficult to evaluate function f into a series of optimization problems for this much easier to evaluate function, this acquisition function. So the hope is that once we loop through this T iterations of optimizing acquisition functions, we can find a pretty good point that gives us very good value for the function f. All right, so I want to talk about these two questions before we dive into more complicated issues. And the first one is the probabilistic model. So in case like people don't know Gaussian process, I'm going to like do a brief introduction on what it is. So Gaussian processes are usually the kind of probabilistic model we use for Bayesian optimization. And it basically describes a probability distribution of the functions. And you can think of it as sort of as an analogy from the Gaussian distribution to describe numbers. And then, well, the Gaussian process is actually a very basic distribution to describe functions. So the only assumption we're using here for Gaussian process is that any finite set of function values is a multivariate Gaussian. So what that means is we have, so all these colored lines are actually samples from the same Gaussian process. And if we just look at one particular line and we look at the function values at different locations, x1 through x3, all these three function values actually follow a multivariate Gaussian distribution. All right, so to be more precise, what we're saying here is that a Gaussian process is defined by a kernel function, k, which takes in two values, two inputs, and then a mean function, mu, which takes in one input. And once we have a finite set of inputs, x1 through xn, they follow a multivariate Gaussian distribution where the mean is parameterized by, well, the evaluations of mean function mu at all these inputs. And then the covariance is described by the kernel functions evaluated at every pair of inputs. And once we have a function sampled from this Gaussian process, we can observe noisy output at any input x tau. So y tau is additive, it can have like additive noise, which is the sum of the f of x tau plus some noise, and this noise is sampled from a normal distribution. All right. So the nice thing about using a Gaussian process here is that we can actually get closed form posterior inference for our GP. So here's an illustration of what it looks like. Here, left has samples from the posterior, from the prior, and then for the prior, you can see well all these parallel lines are samples of the functions, and then we have zero mean and some, well, sort of like uniform standard deviation. But once we observe some points like the dotted points, we are constraining our functions to have those values at those dotted points, and hence we're getting very different variance predictions and mean predictions, and all of these are in closed form. Okay, so going to talk about the other part of the question, which is the acquisition function. But in case anyone have questions, here is probably a good place to pose. I'll probably pose around a few seconds. No questions? All right, so let me dive a little more into the acquisition function part, which is actually a very critical part of Bayesian optimization, because this is where we make the selection, where we make our, try to derive our strategy. Okay, so all right, we already know we're going to use a Gaussian process, and now here's how we're trying to do acquisition functions. Okay, so the first example I would like to give is GPACV. It stands for Gaussian Process Upper Confidence Bound. And to me, I think it's a very interesting approach that makes a lot of sense. So here's how it works. We're assuming that, we have a prior, which is the Gaussian process. And then at each iteration, we're going to predict the posterior. And once we get the posterior, we're going to pick an input by optimizing the upper confidence bound. And the upper confidence bound is defined by the combination of the mean function and the standard deviation prediction. So both of them are posterior. And so just to show an example of how this works, we have, so here we have a function which is in red, and the mean function is in blue. And our posterior, our standard deviation prediction is in gray. So in the first iteration, everything's sort of similar. So it's going to pick a random point. And once it sees, oh, this is how well this particular point does, it's going to look at the upper confidence bound. And in this case, it actually ends up at this particular green point. So it's going to think that, okay, if I'm being very optimistic, then this point is really going to give me a very good value. So it's going to query this point, and it sees that, oh, it actually didn't achieve the desired value I wanted. But it still gives me some information about how this function works. So it's going to look at the upper confidence bound again, and still being very optimistic and tries to evaluate more points. It's going to repeatedly do this particular process, and as you can see, the upper confidence bound actually, well, the max of the upper confidence bound actually shifts quite a bit. And as we continue to do this, we may end up evaluating the boundary, but eventually we look at the place where it actually achieved the global optimal. Once it achieved the global optimal, the interesting thing here is that because the parameter that we use here, which is 3, which is trading off between the standard deviation and the mean, actually thinks, oh, somewhere else might also have a much higher value. So it's going to evaluate, and then realizing that, oh, actually it's not as good as the one we've seen before. And this is when it starts to realize, oh, this point is really good, so let me stay around here. It might not keep staying around here, because once we reduce this the uncertainty around this point, it's going to think, oh, somewhere else might have bigger value. But okay, eventually, all right, we're at this point, and eventually we're going to end up at our global maximum. All right, so here is roughly how GPACV works. You can see very simple, very straightforward. The idea is very simple to understand. So some other examples. So this particular one is called probability of improvement. And we're sort of asking the question, once we have the observations, maybe we can evaluate the improvement, the probability of improvement. It's like exactly what the name means. We're going to evaluate the probability of improvement, and as the acquisition function of our Bayes-Opt approach. So in this case, what we're doing is we're looking at the probability that f of x is improving upon the best observation, which is the max of y tau. So tau is from 1 to t. As an illustration, if you look at this particular plot, basically what we're seeing is that recall that our function f of x, if we just look at one single point, it's a Gaussian distribution. If we look at multiple points, it's a multivariate Gaussian distribution. So here we just look at one particular point, f of x, and we're going to, cut our distribution at max of y tau. And then we take a look at all the probability that the function f of x is improving upon this max value. And then we're using that as our as our acquisition function. And this also makes a lot of sense, right? Except that it sometimes doesn't work super well in practice. So what people do is to add a small epsilon to this max of y tau to give it more power to sort of explore. Okay, so another very similar acquisition function, but a lot of times behaves rather differently, is expected improvement. And oops, sorry for the animation, but all right, so here we're doing something quite similar to probability of improvement, except that here we're looking at the expected improvement, which is integrating our function f over the improved area. So because everything's still Gaussian, we can still actually get a closed form evaluation of this particular expected improvement. So, and then in practice, in fact, a lot of times expected improvement shows up as more robust than probability of improvement. All right, so these are some what people might call heuristics, because they're like strategies that people come up with, which sort of make sense intuitively. But one strategy that really stands out to be more sort of principle, or depending on how you define it, is entropy search. So entropy search actually have a lot of methods that extended from this particular method. So for entropy search, what we're looking at is the mutual information between the point we're going to query and the location of the global optimal. And of course, given our observed data. So here are two particularly interesting extensions. One is the original entropy search. So this is because we use one particular form to write out our information game. So H here is the entropy. So it can be written as either the difference between the entropy of A and entropy of A given B, or the entropy of B and entropy of B given A. So for entropy search, we're doing, well, the entropy of the point, the location of the global optimal, and the location of the global optimal given our data, given our new point to query. And for another method is called predictive entropy search. So in predictive entropy search, what we're doing is that we're trying to look at the other form of the mutual information, which is the entropy of our point to query and the difference between the entropy of point to query and the entropy of the point to query given the location of the global optimal. So these both makes a lot of sense, because eventually what we're doing is that we're trying to collect information in order to find the global optimal. So we already have the tools in information theory or probabilistic theory, which says that, well, let's look at the mutual information, and we're going to simply do that. So the only approximation they use here is that they're looking at one point at a time. But if we're trying to be really accurate, then we will look at a set of points at a time. But then, of course, as you can see, well, if you use a set of points, the information gain is going to be very difficult to compute. And even for this one single point, we still need a very heavy approximation in order to get the values we want. So another method that I would also like to talk about, which is also an extension of these ideas, is to instead of look at the location of the optimal, we look at the global max value of this entire function. So here, what we're doing is that we are moving from the d-dimensional input space, which give us actually quite a lot of trouble to approximate what this information gain is. And we're moving from that to the one-dimensional output space. So in this case, well, both values, the y and y star, are actually both one-dimensional, and it makes it a lot easier to compute what the information gain is. And the sort of thinking behind this is that, well, although we care a lot about the location of the global optimal, if we get the information about the max value, potentially we're still getting a lot of information about the location as well. Okay, so for this particular acquisition function, again, we can write out the information gain. And then what we see is that the first item is simply the entropy for a Gaussian. So because Y is a Gaussian distribution. And then the second item is, well, it can be approximated by the entropy for truncated Gaussian, because we know that our our function value Y must be smaller than or equal to the global max value. So both of the terms have a closed way of computing it, and you can eventually write it out in closed form. All right, so just to give you a brief sense of how it works, if we try to, okay, so actually I forgot to show this. So here, eventually, we're going to compute this closed form acquisition function by summing over the samples of max values from a set. And the main question here is how we can sample it. So here's a very simple idea of how we can do that. We know that at each point, we are going to have a Gaussian distribution. So, although this theorem doesn't exactly apply, but we also know that the maximum of a set of IID Gaussian variables is asymptotically described by a Gamma distribution. So although it's not IID, and we can still try to sort of assume, well, assume if they're IID, we can actually approximate the max value of the representative points by a Gumbel distribution. And then sampling from that Gumbel distribution is very simple. Okay, so this is one idea. And in fact, it's also performing quite well than the predictive entropy search method. So both the predictive entropy search method and this max value entropy search method uses samples. So we're looking at samples from 1, 10, and 100. So for PES, it's sampling the location of the optimal, and then for MES, it's sampling the max value. And what we can see is that as we increase the number of samples for PES, the performance is increasing, but for MES, it sort of didn't really matter. And then one more good thing about this approach is that we can have very low runtime. So computationally, it's very cheap comparing to other entropy search methods. All right, so and one more important reason that I'm talking about all these acquisition functions is that there are actually some very interesting connections beyond them. So for the MES approach, if we just look at one single example, one single sample of our max value, we can actually see that it's a function of this gamma y star of x. And if we plot out the relationship between alpha t, which is our acquisition function, and gamma y star, we are, they're actually monotonically decreasing, which means that optimizing the acquisition function is equivalent to minimizing our, this particular function gamma y star of x. And so interestingly, this actually also leads to some connections to existing methods like probability of improvement and upper confidence bound. So in fact, for probability of improvement, it is also minimizing this gamma function by switching this y star to the max of y tau plus some epsilon. And then for the GPACV approach, this is actually also minimizing our gamma function, except that it's using this parameter, which is the max, which is actually the maximum upper confidence bound. So they're all equivalent to minimizing this y theta of x if under different circumstances of what theta is. So this actually also carries over to the upper confidence bound approach. We can show that by switching what this beta parameter is, both MES and PES are doing exactly the same as optimizing an upper confidence bound, except that they're doing this under different special cases of what beta is. Oops. So, so if you are going to look at Bayesian optimization research, one thing you're going to see a lot is the regret bound. And what this regret bound means is that we're trying to characterize how well we're doing in Bayesian optimization by looking at the regret. Here, so there are several different ways of defining the regret, but here I'm using the difference between the maximum value of the function and the maximum value that exists in our observation. Okay, so so here is roughly an overview of what these two different papers are saying. So for if we assume that our function f is a sample from the GP, then our GPACV approach will obtain this particular regret bound. So notice that here we're using the Gaussian kernels. It's okay if you don't know what it means, but other kernels might be a little different. So I think the interesting thing to see here is that so D is the dimension of the input, and as we increase the dimension of the input, we're actually going to get a worse regret bound. And for MES, it's doing something pretty similar. They also have an exponential dependency on the dimension, but then the other terms are a little different. So anyways, these are sort of like the typical regret bounds that you may see in different papers. And actually, a lot of times, the regret bounds are derived in a similar way to the GPACV method in Srinivas et al. All right, just to summarize how this up works. So we have posterior estimation, and then we're going to define acquisition functions. There are a lot of them if you look at the literature. And then we're going to evaluate this function f at our points that achieves the best acquisition function value, and then we're going to repeat. So this is basically the process that you need to know in order to understand these kind of methods. Okay, so for, I don't know how much time I have left, but I don't think we're going to cover all of these topics. So for some of these topics, I have the slides for some others, I'm like the auto constraints, I don't have the slides, but I can still talk a little bit about it. I believe the organizers are going to bring up some questions.
Yeah, we are going to do that right away. We are going to launch Slido, where you can select which talk you want to, which topic you want Z to cover now. All right, so please vote for the topic which is most interesting for you. So it seems that we are approaching the winner, and I think we can close the poll right now.
All right, let's talk about robotics. It's interesting to see that people are very interested in robotics. All right, let's go. So I must say that my PhD was actually in machine learning and robotics, and it has a pretty big emphasis on robotics applications. So actually, we don't call it robotics applications because what we're really doing is that we're trying to solve robotics problems. And then it turns out Bayesian optimization is a very nice tool to deal with some of the problems. And that's how I sort of started doing more research in this area. All right, for robotics, we definitely need some videos. So here, it's actually part of my PhD thesis. The robot, which is a PR2, is trying to deal with a long horizon task. I forgot what it is. Oh, it's trying to cook a broccoli, and that green little thing, the box, is what we used to call broccoli. And then it's going to cook it and then serve it on the plate, and then return it home. So here, the second task is that it's trying to make a cup of coffee. It's going to pour the coffee, to scoop some sugar. Of course, they're not really sugar. And then it's going to stir it, and that's done. So, right, so, well, we can keep it playing. So the reason I'm showing these two simple examples is that I just want to tell you that a lot of robotics tasks that we really care about are actually very complex, very long horizon. They can be stochastic because the robot arm, when it's executing, it's not doing exactly the same action or same control as it used to. So it might place, like for the same placing action, it might place the object slightly different than where it placed it before. And in these particular tasks, we're also assume everything's fully observable. So that is to say, the robot knows exactly where things are, including the balls, the cups, the green blocks, and it's where it is. So the reason that we're making that assumption is, well, is exactly to make our lives easier, because doing partially observable actions, well, doing partially observable states is a lot harder than the fully observable one. And if we can't do all these complex tasks in fully observable cases, there's little hope that we can deal with the partially observable case. All right, so there are a couple of questions in how to accomplish these tasks. The first one is that we need to enable the robot to have like skills, which means it needs to know how to push, how to pour, how to grasp, how to place. And for each of the skill, we need to have a way of enabling it to learn how to do things. In our case, we want to do this so that the robot can start from anywhere, and then it can go to a goal position that's specified by us. So one problem here is that a lot of these skills are multimodal, which means that we repeat the same one, but it ends up at different places. Excuse me. All right, so here's how we're doing this, very roughly on a high level. Suppose we have a starting location S and the goal location G. The thing we're trying to do is that we're trying to select what the action is in order to go from start to goal. And that might involve several smaller actions. So here the action means, well, we're taking one little step, you know, and we can't really take that little step from start to goal. So the one very simple way of doing this is to think of it using like a reinforcement learning framework. I mean, by reinforcement learning, I really mean dynamic programming. So if you don't know this this function, that's okay. But if you know it, it's basically the like the Bellman updates, and then we're going to select our action by optimizing this particular function. But in our case, this particular function involves the transition from previous state to the current to the next state, and this particular transition will be computed based upon our collected data, and this will be computed only on demand, which means evaluating this function actually becomes quite expensive. But then, yeah, coincidentally, we just talked about optimizing expensive functions, right? And what we can do here is that we can solve this by Bayesian optimization. All right, so here's a little animation on how this works. Don't blink. So we're going to we're going to select the actions by optimizing this function repeatedly at different states. And then once we reach the goal state, we're going to use the real-time dynamic programming approach and then backtrack to update the values for each state. So for this real-time dynamic programming approach, we're actually doing this repeatedly. So it's optimizing this function repeatedly, and then every time it will actually go to a different. It might use a slightly different action because our actions are stochastic. All right, and then eventually, once we repeat this enough, we're going to be able to update the values for the states that it's going to encounter if it's trying to travel from start to goal. And then once we deploy it, it will know at each particular state where to go. Oops. All right. So here's so that's pretty much like how we are trying to learn the skills, but there could also be like other approaches, which I'm not going to cover. But then another big question is, how do we plan with the learned skills? So what we talked about is just one single skill, but it's eventually, once we try to do the long horizon task, it's a very complicated, well, it involves very complicated combinations of actions or actually of skills. All right. So here's what happens. Like a robot might be trying to like make a cup of coffee, for example, and then it sees that on the table there are several different tools it can use, and it's going to start thinking, okay, from my current state, if I do this and that, pick up, push or pull, where do I get? And it's going to think in like a tree-styled search approach. And then eventually, if it hits the goal, it will take that particular route. So a question here is, our skills here actually involve continuous parameters. And in order to do tree search, we need to sample them. And then another question is, how can we do tree search on both the discrete and continuous variables? So the second part is actually handled by an approach that I didn't cite here, but it's from my lab mate, Ken and Garrett. And it's basically doing something like that. And our key question here is really how to sample the scale parameters for our planner. So this is assumed that we already have a planner that can deal with that, which actually we do already have. So here we go from the pouring scale, and then there are some continuous parameters, x. So again, it's very similar to the Bayesian optimization setting. We are trying to evaluate how good these continuous parameters are in order to decide which one to train next. So yeah, that's all. That's like another example of how we're using Bayesian in our robotics problems. All right, cool. Okay, so actually that's my last slide for the robotics part. I'm not sure if we have more time for other topics, but I'll try to. Okay, 2 minutes. So, all right. So I just want to tell you a bit more about what's going on, like sort of at Google, and we actually recently had a Google Bayesian speaker series, and we are releasing all the videos, and 4 of them are actually already online. So you can search Google Tech Talks on YouTube to learn more about what's going on in this field. Actually have, well, a talk from Andres Krause and also Yasha Bengio. They're all talking about really, really interesting topics. And if you like this talk of tutorial, I'm sure you can understand all of them. All right. So yeah, let's see if we have any questions.
Yeah, we have a few questions, so we can go to the Q&A part right now. And let's start with a question from Dimitri. He asks, Gaussian processes are often expensive to evaluate when there is a lot of data. Can we use alternative methods, e.g. ensembles? And if yes, what do people prefer to use in practice?
Yeah, that's a very good point. And that's actually something a lot of people are thinking about. So can we use ensembles or even like Bayesian ensembles, Bayesian neural nets in order to make this process easier? So so my take on that is, I mean, you certainly can, but then the problem is for the ensembles, once you get a new point, you have to update it. But training ensembles is very difficult. I mean, it takes a while. In my understanding, it takes quite a while. So in order to use ensembles to just update one point is not very economical. And so what people typically do is that if we're in the batch large scale setting, then it might make more sense to do ensemble approaches. So I actually do have a slide on that. Oh, all right. Let me try to find it. Window. Okay, cool. So on the left, there's a Longframe process, which is actually also an ensemble approach. But we're only using it for the a batch of queries instead of one query, because I mean, in this case, so for Mandarin process, it's actually not super expensive to update one example, but still it works. It sort of like work very naturally for batch queries, because for each ensemble, you can, well, for each member in the ensemble, you can sort of predict one query to evaluate, and then if you aggregate from all the ensembles, or all the members in the ensemble, then you can get a batch of queries, and it works very naturally with that. Yeah, that's it.
All right, I think we can move to the next question. So Robin is asking, so how do you choose the prior?
Oh, interesting. Yeah, I also have a slide on that. Actually, a topic on that. There are a lot of, I mean, there are, can we, okay, let me try to share it again. Can you see this here? Okay, thanks. All right, so this is a whole different topic. I mean, they're super related, but there are a lot of questions on where do we get the prior, and if we don't have a prior, how do we get the regret bound? And if you really look at this type of problem, it's sort of like a chicken and egg problem, because we're, in practice, we're estimating the prior from the data, and then we're collecting the data based on our prior. And I mean, I think it creates a lot of issues. And in fact, I think a lot of people actually do also think like that. And there are some methods to try to alleviate this issue. And this is actually something I'm still working on. One particular potential solution could be that we try to do this by learning this prior from the similar functions. So similar to estimating a Gaussian distribution, we can estimate a Gaussian process if we have enough examples. And in this case, examples mean function examples. So if we try to do that, I mean, all right, there are a lot of different names for this. If we try to do that, I'm going to skip those. But eventually we can actually also reach a regret bound, which doesn't require the fact that we know the prior. There's no assumption on this prior, or this Gaussian process is known ahead of time. Yeah, so that's like my method of doing this. But I think a lot of people have other approaches. Like, for example, I believe there were papers where you can adapt the length scales of length scale based kernels, and then you sort of like decrease the length scale bit by bit so that you're still encouraging exploration. Yeah.
All right. Can we move to the next question? Yeah. So Auxis is saying, fun fact, did you know that Professor Jonas Moskus, who coined the term Bayesian optimization and introduced expected improvement acquisition function in 1978, worked in Vilnius, Lithuania?
Sorry, worth what?
So Auxis is just sharing this fun fact that the professor who invented the term Bayesian optimization and introduced expected improvement acquisition function actually worked in Vilnius, Lithuania. There we are doing this machine learning workshop today.
Oh, interesting.
Yeah, just a fact for trivia.
Yeah, I guess people there can talk to him.
Let's move to the next one. Why we care about the regret bound? Is it related to the online learning?
Regret bound, right? So why do we care about the regret bound? I mean, that's actually a good question, because a lot of people don't care about the regret bound. And so, I mean, I think, like, to me, so when I was in my PhD, actually, now my advisors cared about the regret bound, but we still had a, because I mean, because they sort of didn't really care because, I mean, they're roboticists. And they always thought of me as a theoretician once I showed them, oh, here are the regret bounds. But I mean, I think the real reason is that I believe we need some kind of certifications for machine learning methods. This certification can come as a regret bound. It can come as well, something that sort of like guarantees, oh, how well I can do once I achieve a certain, once I reach, like, say, a certain level of data collection. And I think it's super necessary for a lot of scenarios. So personally, I worked a little bit on autonomous driving before as an intern, and I realized, like, it's really important that we have certifications for our methods. And this is something like machine learning really lacks. Like, we can definitely get a lot of theoretical guarantees, but all these guarantees require some kind of assumptions, and they don't really match real-world scenarios. So I'm not saying that this is, like, if they don't match, then we don't do it. I think these are just like graduate steps that we try to take in order to finally reach a step where we can say, oh, if I do, like, say, X-rays of patients, then I'm guaranteed to be like 99% accurate, or I can provide some kind of interpretation about why I'm making a mistake. So all these sort of things, I think, sort of comes to this question of what kind of certifications can we make for machine learning methods. But yeah, we're just taking like baby steps right now.
All right. I think that's all the time that we had for questions today. So thank you very much, Z. And I hope that you had a good time. I hope that everybody, all the participants had an interesting time listening to your talk.